Hello everyone, welcome back. Chapter 8.5, Acid Catalyzed Hydration. Let's keep in mind, this is a Markovnikov addition. So in Markovnikov, for recall, whatever I'm adding, whether it's a bromine, iodine, chlorine, or in this case an alcohol group, is going to go to the more substituted side, and the hydrogen going to replace the least substituted side. So let's give this a look. First of all, in acid catalyzed hydration, acid is used but regenerated, and that's how you know you're going through the right track, when you regenerate your acid. So first of all, I'm adding alkene to hydronium, one of the simplest acids. What's going to do, this alkene going to come and attack my hydrogen, going to extract it away from hydronium, leaving this water by itself. And just to keep in mind, this is an aqueous solution, there is an acid, but the majority, what's excess in there is the water. So when this alkene breaks, my result is something like this, right? And my carbocation is on the more substituted side because it's Markovnikov addition. I'm left with, after this hydrogen gets extracted from the hydronium, I'm left with the water right here. This water would come and attack because I have a lone pair of electrons, which they are negative, and I have a positive side right here. My result should look as this. Right. Remember, I'm in a medium of full of water. Water is excess. I have water molecules are coming around still, floating around, wondering what they could do and what's their job. So what's going to happen is actually this lone pair of electrons is going to come and extract this hydrogen away from this water. Result is plus now check this out. I added my alcohol group, right, to the previous alkene, and I regenerated my hydronium when I first used it. Acid is used but regenerated. Hi. Chapter 8.6, oxymercuration and demurcuration. So what does oxymercuration means? I'm adding oxygen with mercury, and I'm going to demercurize it again. That means I'm going to extract that mercury again from the solution. Going to leave me only with alcohol group. Why this is beneficial? This is beneficial because if I use this in lab, if I use this technique of adding an alcohol group to my alkene, it wouldn't do a carbon rearrangement. And what I mean by carbon rearrangement, let's go previously to chapter 8.5 when we were doing the acid catalyzed hydration. When I had an alkene, I added an acid to it. Let's just do another example of it, and I'll show you what it means by you getting a carbon rearrangement. Let's say I have something like this, right? And my alkene is right here, and I'm adding it to hydronium again. Now this alkene would come and extract this hydrogen, right? This hydrogen would break. My result, I'm going to write it here down, is going to look something like this, right? Where it was also Markovnikov addition, so my hydrogen got added to this side and my carbocation would result here, right? But keep this in mind, this is tertiary carbon, right here, this carbon is tertiary, connected to a methyl group here, and a carbon chain here, which is an ethyl. I have an hydrogen here, right? What would happen is, because it is more stable to form that carbocation on a more substitute side, the hydrogen would come towards that carbon, resulting in my carbocation got on the more substituted side, and my H2O gonna come and attack here, resulting in So that's the carbon rearrangement. When I use oxymercuration-demurcuration, there won't be carbon rearrangement because the intermediate will be a mercanium ion. So this is the mechanism for the oxymercuration-demurcuration. Remember what I just said. This is beneficial because it will not form carbon rearrangement. So what happened in this mechanism is that alkene attacks the mercury, but this is all considered mechanism. This like an SN2 mechanism where this lone pair come and attack that alkene also at the same time and break one of the bonds with the OAC. So what form is, we call this a motif right here, where is kind of like a ring, 3 bond rings to the mercury. This and my water, this is an aqueous solution, of course. So I have in my medium, I have water in my medium. The water would come around and it would attack the more substitute side because this is the most stable. So these lone pairs would come and attack here towards the more substitute side, right? And breaking that ring and give those electrons back to that mercury because we don't really want mercury to be positive. Imagine mercury is positive, that's very dangerous. Anyhow, we go back. This bond got broken and I've got my H2O attached to the molecule that I have. I still have water in my medium, don't forget about that. That water would come and extract the hydrogen because oxygen is positive here, and do we like oxygen positive? No, we don't. And then this bond would also break and give those electrons back to the oxygen. My result is this H got extracted. I'm left with an alcohol group right here, OH, and I have my mercury right here. This is beyond the scope of our class, and you really don't need to know it. You're only held accountable for the mechanisms from this step all the way to here. But you don't need to know how this Hg would leave, because that mercury, some miracle happened and it would just go away and leave us with the final answer, which is this. This is beneficial because you could always use it and would not form a carbon rearrangement whatsoever. So it's more used in lab. It's not the most green thing to use, but it's beneficial.